Okay, going to wrap up the chapter. One thing I want to mention that's going to come up later is a concept called reradiation. And the electrons going around a nucleus have frequencies, they have vibrational frequencies. So some electrons will react to some frequencies of energy and not other frequencies of energy. So certain frequencies of energy hit a whole bunch of atoms, but only a few of them will absorb the energy. It mostly is picked up by the outer electrons, and when you pump energy into them, they go faster, and when they go faster, they can't stay in the same shell, they jump out. So now they're in a shell all by themselves. Now with certain ionizing radiation, they jump completely off, is that they form ions. But for other types of atoms, they jump out, they can't stay out there, they're not stable, but they don't have enough energy to get free, so they pretty quickly jump back down where they were. And they have to release energy to do that. Well, the transition has changed the amount of energy in the whole system. So energy comes out at a different frequency than it went in. They re-radiate, and we can actually detect in space the composition of the dust between us and a star, because some of the frequencies from the starlight get absorbed by the dust. The energy comes back out, but it's not the frequency it left the star at, it's a new frequency that's particular to those atoms in the dust, which tells us that the dust isn't just rocky material, that it is organic material, a lot of it is, that there's water out there. And that's one of the ways that we originally figured out what primordial soup was made of. We'll talk about that later. Last thing for this chapter, coming back to isotopes. In nature, most of the carbon is C12. A small amount of it is C13, and a small amount of it, but a little bit more, is C14. Carbon dioxide in the atmosphere, or C14 carbon dioxide, is generated in the upper levels of the atmosphere. Energy comes in, interacts with atoms, and you wind up with carbon 14 as an isotope in carbon dioxide. And then it comes, through mixing, it comes back down to this level. So at any given moment, a certain fraction of the carbon dioxide around us has got radioactive carbon in it. It's not super radioactive, but it's radioactive. Now we don't absorb that directly because we don't breathe in carbon dioxide, but plants do. So plants take in the radioactive C14 and incorporate it into their molecules, right? They make glucose through photosynthesis, and then it becomes part of a bunch of stuff. We get it when we eat the plants, or we eat something that ate the plants, or eat something that ate something that ate the plants. But this fraction of carbon 14 in biological material works its way up through the food chain. Carbon 14, because it's unstable, it decays. It decays through beta radiation. And because it decays through beta radiation, it releases an electron, and it changes the element, because it's no longer carbon. It's no longer carbon. It's now nitrogen. And the nitrogen is no longer locked in the molecules, it comes free as a gas. So over time, the carbon 14 that was in there originally, once something dies and no longer is integrating this into their tissues, is that the carbon 14 breaks down into nitrogen, and the nitrogen goes away. How fast does this happen? How fast something changes on a number of different levels can be a half-life, which basically is a measurement of, okay, we have this much to start with, how long before there's only half of it left, for whatever reason. You can do a half-life for things that you take into your body, like vitamin C. You take in vitamin C, the amount that was in your food, how long before only half of that is there? It turns out there's just minutes. It flushes out, your body integrates some of it, and you flush most of it out through your kidneys. And then it's gone. It's no longer part of you, it's just part of your urine. That's a very short half-life, but that's not radioactivity. Radioactive half-life is how long, if you start with this radioactive material and it changes into something else, how long before the amount you started as, there's only half of it left. And for carbon-14, the half-life is 5,730 years. Now you start with a very small amount, like I have carbon-14 in me. I don't have a lot of it, but I have a predictable amount. In about 6,000 years, there'll only be half of it left. Another 6,000 years, there'll be only half of that left. And another 6,000 years, there'll only be half of that left. So you can see, it's dropping off. This is thousands of years. Now, if we pick up something that was once alive, and we can measure the amount of carbon-14 that's still in the tissues, we can take a pretty decent estimate of how long this thing has been dead. That's carbon dating. You call it radiometric dating. We can do it with other materials too. Carbon dating, by the time you're about 60,000 years in, there isn't enough of it left. You can't get a reliable enough measurement to take a pretty good guess as to how long the thing has been dead. So for things from the ice ages, that works fine. For things that are older than that, then you're looking at dating radioactive materials in the sediment that's settled around the dead things. Radioactive uranium and argon, and there's other sorts of ways to measure age past the 60,000 year threshold. This ends at 50.4. But yeah, up to about 60,000, you can kind of still take a pretty decent guess. So we can estimate the age of a mummy sarcophagus, or the Shroud of Turin, which doesn't date back to the time of Christ. It dates back to the Middle Ages, when weirdly enough, painting these weird burial shrouds was all the artistic rage. People tend to forget that the Shroud of Turin wasn't created in a vacuum. It was part of an artistic fad at the time. But they put it into a church, and at some point they went, well, that's what Christ was wrapped in, and somehow he had magically produced his image on the shroud, but the shroud only dates back to, I forget, 1100, 1400, something like that. But that's because we can measure, the shroud was made out of cotton, biological material. You can measure the amount of C14 that's left in it. Okay, that is chapter 1, is that how atoms, we haven't really gotten into molecules yet, but we will get into molecules in the next one.